Hello everyone, welcome to our video lecture. So guys, in this session we'll continue with our last topic, right? So I think we have discussed about chirality in our last lecture, about chiral center, about chiral carbon, about prochiral carbon, and then we started about the properties of chiral center and chiral compounds, right? We have discussed that if a compound is optically active, means it will be unsymmetrical. Okay, so for one chiral center compound, if a compound is having one chiral center, then it must be what? Chiral means unsymmetrical, means optically active. Okay, so we discussed that if the compound is chiral, so that compound will be having optical isomerism. So the optical isomer of that compound will be its mirror image. And both the compounds, one compound which is chiral and the other its mirror image, they will not superpose each other. Means this compound having the atoms will not superimpose with all the atoms of this compound. Means each and every atom cannot coincide. And I think that two compounds, as I discussed in last class, the term used is enantiomers, right? So the compound, optically active compounds, its mirror image is non-superposable, and in that case these two, the pair will be called as enantiomers. Okay, so let's continue with the same question. I think I have told you about one question. And the question was carbon having hydrogen, deuterium, tritium, and here it was fluorine. Okay, you can check out in your notes, you must have written all the things of our last lecture. Check this one. So we have here carbon having hydrogen, deuterium, tritium and fluorine. This is a chiral center. As we have one chiral center, so we can say it is not having POS, no COS, no symmetry, and hence it is chiral compound, optically active, no symmetry. Now if I draw a mirror image, what will happen? Carbon with hydrogen here, tritium, this fluorine and deuterium will get exchanged. Now if you remember, I have told you to understand or imagine this part in 3 dimensions. Okay, so let me explain you in the best possible way. Suppose if I say this carbon atom is having hydrogen atom in this plane only, okay, like this, and this tritium like this, okay, this side, okay, then you can say this one tritium and this one hydrogen. So if I choose this plane containing carbon, hydrogen and tritium, then I can say here that this fluorine and this deuterium must be backside, means hydrogen this side, tritium this side in 109 degree approximately, okay, because it is not perfect tetrahedron, all the 4 atoms are different. So tritium this side, so that fluorine must be like that, backside, and this deuterium like that side. Okay, so when we draw mirror image, what happens? This hydrogen was like this, here it will be also like the same. Tritium was like this, here also it will be same. But when you say this fluorine was that side and deuterium that side, so due to mirror image part, fluorine will come this side and deuterium that side, but at the same time both will be on backside only. Okay, now guys, let's understand. If I pick this compound, okay, hold it compound and keep it here, what you will find? This carbon will coincide with this carbon, that is okay. This hydrogen will coincide with this hydrogen. Also this tritium will coincide with this tritium. But as we know, this deuterium and fluorine, here deuterium is this part and deuterium here this side. So these two atoms, fluorine and deuterium, will not coincide with each other. Okay, so when all the atoms cannot coincide, then they are not superposable and hence they are enantiomers. Okay, now let's see what can be done. Suppose if I invert this molecule, if I hold this compound and invert, what will happen? This carbon will be at the same position, means bonding will be same, but observe in 3 dimension. Earlier this tritium was this side. If I hold this and invert, earlier this is like this, suppose I invert totally 180 degree, what will happen? This fluorine and deuterium will interchange. Obviously fluorine will come this side and deuterium will come this side. But again let's observe in 3 dimension. After inverting 180 degree, carbon and hydrogen will be at the same position, which can superpose, means they will coincide with each other. But in this case tritium is towards like this, and this one on inversion means rotation to 180 degree, that tritium will go that side. Okay, so you can understand tritium will not coincide, although it will be observed after rotation. What will happen? This will be hydrogen, tritium, fluorine and deuterium, but here tritium is towards you and this tritium is not towards you, it is backside, that side. Okay, so this tritium will not coincide, first of all. Now let's imagine here fluorine was towards that side and deuterium also towards that side. So here also it was that side and that side, but when you rotate 180 degree, both will come towards this side. Okay, means this fluorine is towards this side, deuterium towards this side. So we can see in 2 dimension that fluorine here and fluorine here same side, but this fluorine is towards inside, back side, and it is towards front side of the plane. Then you can say this fluorine and deuterium also cannot coincide with each other, and hence they are not superposable. Okay, so this is structure number 1, this is structure number 2. We can say structure 1 and 2 bear non-superposable mirror image relationship, and hence are enantiomers. Okay, so these two bear mirror image, non-superposable mirror image, means all atoms cannot coincide with each other, so they are enantiomers. Okay, now friends, understand what are the properties of enantiomers. First of all, properties of enantiomers. Okay, first property, enantiomers are optically active substances. See, this is the most important part. They are optically active substance. Means if a substance, you are asked whether these two substances are enantiomer or not, first of all check whether the compound is optically active or not. If it is optically inactive, then there is no sense to talk about enantiomerism. Okay, second, physical properties are similar. Means a compound and its mirror image both are optically active, they are enantiomers, then their physical properties will be same. What are the physical properties? For example, boiling point, melting point, density, refractive index. Okay, almost these all physical properties are similar in enantiomers. Now generally we can say they exist in pairs. Generally we can say, because if you have one compound optically active, then its another form will also be there. Both will be optical isomers of each other. Next, chemical properties are also same. their chemical properties will also be same. Because suppose if I say a compound having alcohol, okay, means the functional group in that compound is alcohol. So its mirror image, that enantiomeric pair, will also be alcohol. So the properties of alcohol bear the same for both the compounds. Okay, so chemical properties of both the compounds will be same. Although remember this thing, there may be variation in rate of reactions due to different sites. Okay, the two sites are different, so the rate of reactions may vary in two enantiomers. Okay. Fourth, biological properties differs. Now friends, what are biological properties? For physical properties, you know, melting point, boiling point, refractive index, density, and all these cases which relates to their physics, okay, appearance or like that. Now chemical properties relate to how it behaves with on reactions, means its reactions, rate of reactions, whether it will react with one compound or not. These are all about its chemical behavior and chemical properties. Now when we say about biological properties, it simply means in the biological phenomena. Let me give one simple example. If I say plus sugar and minus sugar, now what is this plus and minus? Sugar for organic compound sugar, but when I say plus and minus, means optically active having clockwise rotation then plus sugar, and levorotatory minus symbol L, that is for anti-clockwise rotation of PPL. So plus sugar and minus sugar, I am just giving an example. When we observe plus sugar, it plays a very important role in animal body. In animal metabolism, plus sugar plays a key factor, okay, inside the body, animal body. But when we say minus sugar, it has been observed that it has no such significant role, no role as such. So when one enantiomer plays an important role and other has no role as such, so the two pairs of enantiomer will be different in their biological activities. Let me give you another example. If you remember my first lecture of optical isomerism, I told you about one compound, limonene, if you remember. So when I say limonene, there was plus limonene and minus limonene. Plus limonene was one of the enantiomer which was found in oranges, while the other minus limonene was found in lemons. So you can understand, just due to that mirror image relationship with optical activity, their presence or their activity or their metabolism are different. Clear? Okay. Now let's observe this compound. Okay, as we know that this compound is having carbon with fluorine, chlorine, bromine and iodine. This is one chiral center and this compound is optically active. Okay, now the question arises, what will be its enantiomer? Means its enantiomeric pair will be what? So just draw the mirror image of this compound. Okay, as it is also optically active and the mirror image will also be optically active. So the mirror image of this compound will be fluorine and iodine remain same, but this bromine and chlorine will be interchanged. Okay, so here I told you in terms of this Fisher projection. Okay, this is your vertical line, this is your horizontal line. So if I place the mirror this side, so this horizontal line is exchanged, and if I place mirror this side, so what will happen? Horizontal will remain same, but vertical part will be interchanged. Okay, now if I say compound number 1, 2 and 3, what happens? Whether you say compound 1, 2 or 3, all are optically active compounds. Okay, now what is the relationship between two? Then if I say 1 and 3, then they bear mirror image relationship with non-superposable mirror images. So 1 and 3 enantiomer, 1 and 2 enantiomer. Okay, clear to everyone? Fine. Okay. Now let's come to the same example we have discussed earlier also. We have discussed in this compound there is no POS, no COS. Okay, you remember this part? From this carbon I have explained this is also upside, this is also upside, so no COS. Okay, so in this if I say that this is optically active, right, PPL rotation occurs from this, then just draw its mirror image. CH3 Cl H H Cl and this is CH3. So compound 1 and 2 enantiomers of each other. Okay friends, so you have understood about enantiomers and you have understood about the properties of enantiomers. Okay, generally enantiomers exist as pairs. Means if I say there will be this compound, then there will be this another compound. But remember, as the biological properties are different for the two compounds, then we can say that the two compounds are different. Okay, in terms of isomers they are same, definitely molecular formula is same, even structural formula is same, but at the same time their properties are different and hence they are stereoisomers, right? Due to arrangement in space is different, so due to properties difference the compounds will be said as two different compounds. Clear? So their interconversion energy barrier is not small. Okay, they cannot interconvert in one another very easily. Understand? Okay. Let's see one important example of 2-butanol. It is studied as an important case. Now you can see here this carbon is attached with ethyl, methyl, H and OH. If I will make numbering, then 1, 2, 3, 4. Butane 2-ol or 2-butanol, right? You can see here that in this compound this carbon is attached with 4 different groups: OH, H, methyl and ethyl. So it is an optically active compound. Optically active, right? Symmetry, or I can say it is unsymmetrical. Okay, now what will be its mirror image? In general terms, if I say that this is this methyl this side, this ethyl this side, this hydrogen and OH, now if you will see the two possibilities of this 2-butanol, then their properties will be different in terms of biological properties. But if I say their melting point and boiling point, it has been observed both are having same boiling points. Okay, as we know it is alcohol, so it will be having intermolecular hydrogen bonding as well. Okay, so with general thing, if I say with having compound with nearly same molecular mass, any hydrocarbon having nearly same molecular mass and this compound, then observing the two, this will be having higher boiling point due to intermolecular hydrogen bonding. Okay, now let's understand the IUPAC part. What IUPAC naming says? IUPAC specifies that if I say the IUPAC name of any compound, then it can be drawn perfectly. But suppose if I say that it is 2-butanol, then I can draw either this one or this one. So these two are actually different. As we have discussed, they are enantiomeric pairs, and if these two are different, then there must be two different names for these two compounds. Okay, so there are particular scientists which studied about this thing and they came to some conclusion that in such cases when there is enantiomeric pairs, then we need to name it in different way. Okay, so they found about two different things. that is RS configuration. Now what is this RS configuration? Let's understand it in detail. RS configuration. Okay. Now, three scientists named Kahn, Ingold, and Prelog. Okay. These three chemists named, one was Mr. Kahn, another was Mr. Ingold, and another Mr. Prelog. Okay. These three scientists and chemists, they studied a particular pattern through which they named the compounds, the same compounds which are enantiomers of one another in different names. Okay. And the term used was R and S. Now what is this R and S? R stands for rectus and S stands for sinister. This is for right, and then you can understand this will represent your left. Okay. Now they specified some particular rules to understand this RS configuration. Means, as we know that the two enantiomer, one compound and its enantiomer, they are configurational isomers. Okay. So simply when we say they are having configurational isomers, so their name is represented by either R configuration or S configuration. So let's understand this part in detail. So what they said a particular rules will be governed, okay, through that rule which is called as CIP, Kahn, Ingold, Prelog, CIP rule for RS configuration. Okay. Now many of you can remember geometrical isomerism part where we also studied about CIP rule. Okay. To decide the priority of groups, if you remember, towards a C double bond C, two groups this side, two groups this side, we decided the priority. Here also some similar type of rules will be governed through which we can name the compounds in different ways. As we studied 2-butanol, so we have two different 2-butanols, right, having different properties. So we can say one is R2-butanol and another will be S2-butanol. So let's see how to make such priority order decision. CIP rule for RS configuration. So this is one of the method of naming enantiomers, okay, to particularly name that particular chiral center through RS configuration. So one of the first important thing is, towards a chiral center only, I will specify whether this compound is R configuration or S configuration through a chiral center having 4 different groups. If it is not having 4 different groups, I cannot say whether it is R configuration or S configuration. Okay. So CIP rule for RS configuration says, first of all, numbering of all 4 different atoms are done as per priority order based on their atomic number. That numbering will be 1, 2, 3, 4. This will be for maximum atomic number. Okay. Means, suppose, see, along with the rules, I am just writing one example. Carbon having fluorine, chlorine, bromine and iodine. Okay. So here you can simply understand that this carbon is having 4 different atoms. So it is chiral center, chiral carbon, single chiral center, optically active. In this, maximum atomic number will be of iodine. So it will be 1, bromine 2, chlorine 3 and fluorine 4. So in this way, we have to make the numbering 1, 2, 3, 4, and maximum priority will be 1, then 2, then 3, then 4. Okay. Next rule. If For first atom, priority can't be decided, move towards next atoms to decide priority. Now what is this thing? I think you have understood this first rule from this example. So I am changing the example now so you can understand the second rule. Now suppose I am telling suppose it is having CH3 and it is having CH2, CH3. Now friends, you can simply see here that this carbon here, this carbon is attached with fluorine, chlorine, carbon and carbon. So atomic number basis, this chlorine will be 1, fluorine will be 2. Now if I say this carbon and carbon, both are having same atomic number. So in that case, you move to the next atoms connected with that atom. Means this carbon is connected with 3 hydrogens. Okay. Now if I say this carbon is connected with 2 hydrogen and 1 carbon. So priority wise, this will be preferred. Okay, so this is considered as 3 and this is considered as 4. Clear to everyone? So when first atom is same, move to next atoms, next connectivity. Okay, clear? I think you have noted these 2 rules. Rule number 3. If atomic number is same, then mass number basis means for isotopes, atomic number is same. Suppose I say hydrogen, deuterium and tritium, then mass number basis decide priority. Example, hydrogen, deuterium, tritium, it is 1H1, 1H1, this is 1H2, this is 1H3. All 3 are having atomic number same, but mass number is different. Deuterium is having mass number 2, it is having mass number 3. So more the mass number, more will be the priority. Clear to everyone? Similar example can be C12, C14. I am giving a few examples which can be used many times. O16, O18. Okay. Fourth, if there is a case of multiple bonds, use hypothetical method of bond breaking. Students, you just write down this rule right now. I will explain you with the help of example. If there is a case of multiple bonds, okay, if there are C double bond C, C triple bond C, then how to check it? I will explain it with the help of example. Use hypothetical method of bond breaking. Okay, next part. In wedge dash form, keeping lowest priority group away from the observer, assign RS. Now what is this? When I draw earlier wedge dash form of 2-ethanol, in that case what happens? If the lowest priority group in dash part, keeping the lowest priority group in dash part means away from the observer, just assign the priority. And with respect to the 1, 2, 3, whether it is clockwise means rightwise, then it will be rectus R. And if it is anti-clockwise means left, means you have to report it this side, then it will be S configuration. Okay, so let's see this thing, this particular thing with an example. See, I am drawing here only, so you can observe this rule particularly. This carbon OH H. See, this was our example. Okay, so students, if you see this example, then with respect to priority, I can say OH will be 1. This is CH2 carbon, CH3. So this is 2, this is 3, and this is 4. Okay. Now, I have made 1, 2, 3 for priority order. Now I can see if I make 1, 2, 2, 3, so it is actually anti-clockwise rotation. Okay, so for anti-clockwise, actually it is left, it is not right. So left, so it will be S configuration. Are you getting my point? Again, let me draw another structure. This is your H, OH. Now in this one, if I have to check whether it is R or S, OH will be 1, this is 2, and this is 3, and this is 4. This is H, hydrogen. So this is your right side rotation. Okay, this is your clockwise. So for right side rotation, it will be R configuration. Okay, so see, these two compounds are 2-butanol, but here I can say it is S2-butanol and it is R2-butanol. Now with this numbering, with this naming, IUPAC naming as per CIP rule of RS configuration, I can differentiate the two isomers, the two enantiomers perfectly. Okay, so you can just check the image, the structure I have drawn for R2, that's true. When I mentioned this 2-butanol structure, you can just check. First one was like this and second one in blue color, it was like this. Okay, so one was S, another one R configuration. Clear to everyone? Okay, so this is simply RS configuration in wedge dash form. Now let's see how to check in Fisher projection. Okay. Find RS configuration. So I am giving you a few simple examples of wedge dash configuration and you have to find out RS. F H Cl Br. Find by yourself very fast. Okay, so in these two examples you have to find whether it is R configuration or S configuration. Okay students, I think you have completed. So let me check the answers. So using the priority rule, fluorine, chlorine, bromine, 1, 2, 3, 4. Now students, understand this important part. When you come across this thing, see, if you move from 1 to 2, you will not find immediately 3. You have to cross fourth part. So that is possible. That is okay. Okay. So to reach number 3 position, you can cross fourth position, or to reach number 2 position, you can cross fourth position. So to reach 2 or 3 from first part, see, first part will be perfect. So from first, if you have to reach second part or third part, you can cross the fourth one. Okay, but never cross third to find second. Means I am just telling, suppose this position would be second. Okay, this position is second, suppose. So you have two opportunities. whether you have to cross 3 to reach second or you have to cross 4 to reach second. So you can cross 4 to reach second, but you have not to cross 3 to reach second. Okay, I'll give it an example. Here it is anti-clockwise, means left, so it will be S configuration. Clear to everyone? Now here I am giving you one very simple short trick to get the answer. Okay, use this logic of SARC. Remember this thing, SARC. S for anti-clockwise, R for clockwise. S configuration when you get anti-clockwise rotation. See, it is anti-clockwise rotation, so it will be S configuration, and R configuration when it will be clockwise. Okay, so simply you have to assign the RS configuration based on whether you find 1, 2, 3 rotation is clockwise or anti-clockwise using the help of SARC, S-A-R-C. Clear? Okay, so it is anti-clockwise S. Now check this one. See, carbon CH2, CH3. This carbon is 1, 2, 3 degree. It is 2 degree. So this is high priority. So this is 1, this is 2, this is 3, this is 4. So in this example, I can simply say it is what? It is again anti-clockwise. So the configuration will be S configuration. Clear? Now check this one. If I see this one, it is having, see this hydrogen and fluorine, okay. This carbon is 3 degree, here also 3 degree. It is having ethyl and methyl. It is also having ethyl and methyl. So students, remember this thing. Sometimes by mistake, you keep trying to get RS configuration and you forget to check that whether the 4 groups are different or not. Here it is what? From this carbon, if I say it is, this group is what? 1, 2, 3. 1, 2, 3 carbon and 4. Okay. Here also 1, 2, 3, 4. Clear? So it is isobutyl group attached with this carbon. So both groups are same. So RS configuration is not correct to be studied in this carbon. Clear? Now come to this one. Here I can say fluorine, chlorine, bromine, iodine. Iodine is 1, bromine is 2, chlorine is 3, fluorine is 4. So it is simply anti-clockwise. So it will be S configuration. I think it is very, very clear to everyone. Okay. So what you have to do, see, in all the examples here, I have taken the lowest priority group on wedge, sorry, on dash, means away from the observer. When lowest priority group is away from the observer, just find 1, 2, 3, whether it is left or right. Right, R configuration, right will be clockwise. So using the help of SARC. Okay, clear? Okay. Now let's find RS configuration in Fisher projection. Okay. Now understand this one. Here also the same rule is applicable. The rule will be decide priority 1, 2, 3, 4. Move 1 to 2, 2 to 3. Crossing fourth group to reach second or third is possible. That it will be okay. Next, SARC applicable, but only if lowest priority group lies in vertical line. Now students, what I have made, decide priority 1, 2, 3, 4. So let's see one by one. Fluorine, chlorine, bromine, iodine. So it is 1, 2, 3, 4. Now move 1, 2, 3. So 1, 2, 3. It is anti-clockwise. Crossing fourth group to reach second or third is possible. Means fourth group, I can cross fourth to reach second or third. Okay, that will take in next example. Let me draw one more example here itself. So it is iodine. I'm just doing what? Now see this example also. Okay. Let me write priority order here. Iodine will be 1, bromine will be 2, chlorine is 3, fluorine is 4. Now you can see I have to reach second. Now I have two possibilities. Either I can cross 3 to reach 2 or I can cross 4 to reach 2. Now the rule says I have to cross fourth group to reach second. Now why this happens? Suppose if I cross 3 to reach second, then I have to move entire portion to reach to third portion. But if I cross fourth one, I can reach here second, then immediately third. So this is the best possible case to move in this way. Means crossing fourth is possible. Crossing fourth group to reach second or third is possible. Now crossing fourth to reach second and then third, that is simple case. Okay. Now SARC. What was SARC? SARC was actually S configuration for anti-clockwise. Now see, this is anti-clockwise. So S, and this is also anti-clockwise. So this is also S. Applicable, but only if lowest priority group lies in vertical line. Why vertical line? As we know, if I draw the wedge dash form of this one, we remember that Fisher projection carries this portion in wedge form in 3D and this in dash form. So simply the lowest priority group must lie away from the observer, means it must lie on vertical line. Okay. So here you can see fourth lowest priority group lies in vertical. Okay. So I can simply say this as S configuration. Okay. Now this one is S because it is anti-clockwise or left, and this one also anti-clockwise and lowest priority on vertical line. So it is this will be also S configuration. I think it is very clear to all of you, right? See, this is one of the most important part if I say about 12th board examination, or if I say about JEE or NEET competitive examinations. In almost all the examinations, if you will see the previous year questions, this has been one of the most important topic. Okay, so guys, learn it very well, use the shortcut trick SARC and understand this thing. Now I am taking a few more examples. Okay, so let's find RS configuration in these two. See, one more important conclusion I'm telling for this example. See, this compound is having fluoro, chloro, bromo and iodo, right? It is having, this compound is what? One carbon having FClBri. This is also having FClBri. So these two compounds, it is also having S configuration, and this is also having S configuration. So if I say 1 and 2, then these two are identical because they are same in all the ways, along with configuration, along with compound molecular formula and structural formula. Clear? Now check this one. Priority first of all, 1, 2, 3 and 4. Now students, what happens if lowest priority group, here it is in horizontal line, so that SARC rule is not applicable as such. So we have alternate method, understand. If I move from 1 to 2, 4 can be crossed, so 1, 2, 3, it is anti-clockwise. For anti-clockwise we have SA, SARC for S for anti-clockwise. So if this fluorine would have been in vertical line, it would have been S configuration, but just reverse the configuration and the answer will be correct. For anti-clockwise, S, but this configuration will be R. Why R? Because here lowest priority group do not lie in vertical line, it lies in horizontal line. And I told you earlier, just interchange any two groups to check the configuration. Okay, that will be your enantiomer pair. So if I interchange fluorine and chlorine, what will I find? Fluorine goes in vertical line. So 1, 2, then 3 anti-clockwise. Okay, so that will be S, its mirror image will be R. Okay, so this is R. Remember this thing, if lowest priority group lies in vertical, SARC is applicable. If lowest priority group does not lie in vertical, then just to check using the rule SARC. If you get clockwise, then the answer will be reverse, S. If it will be anti-clockwise, S, then the answer will be R. Now check this one. 1, 2, 3, 4. Okay, so it is simply clockwise. So clockwise is R, but lowest priority group in horizontal, so it will be S configuration. Okay guys, so here if I compare compound number 1, 2, 3, 4, see molecular formula is same, structural formula is same, only configuration wise 1, 2 and 4 same. So I can say compound number 1, 2 and 4, these three are identical, but all these three are enantiomer of compound number 3. Okay, now see, for this thing also I will discuss in our next video lecture about the properties of enantiomer. What happens when I rotate the compound in 90 degree, 180 degree, keeping one part stable, fixed, and rotate it once clockwise or anti-clockwise. We will discuss in next lecture. Let's find a few more configurations. Okay, so first of all you just find the RS configuration in these three. If you will see, it is actually COH 1, 2, 3, 4, it is actually your tartaric acid. Okay, tartaric acid. So find out RS configuration in this part. Okay, so let's see this one. Here if I see, this carbon is having OH, oxygen here, hydrogen here, this carbon here and carbon here. So for this OH will be first priority, that is done. Now this carbon is having oxygen, this carbon is having oxygen, but with hydrogen and carbon. This carbon is having oxygen and oxygen, so this will be more priority 2. Now simply if I say 1 to 2, it is anti-clockwise, so that is S, but here lowest priority group lies in horizontal, so that S converts to R. So this is your R configuration. Okay, clear? Now check this one. Again I will say OH will be 1 priority, COH will be 2nd priority. So simply I can say in this example it will move towards this clockwise, so it is R, right? Now but R horizontal, so S. I think it is very clear to everyone. Okay, I have used the method of SARC. Again I am telling 1, 2, anti-clockwise, reverse, clockwise, R, OH to COH, clockwise, that is R, but lowest on horizontal, so it is S. Okay, now you have completed this one, check it. This OH will be 1, COH will be 2, as we know. So it is clockwise, for clockwise it is R, but hydrogen in horizontal, so it is S. Now check this one, OH to COH, it is again clockwise. Clockwise is R, but horizontal H, so it is S. Now guys, you can see this configuration is S and this configuration is S. Okay, now if I see, observe this compound number 2nd and compound number 3rd. Actually compound number 2nd and 3rd are compound, and second bear mirror image relationship. You can observe it very well. COH and COH is at the same position. Okay, this COH and COH at same position, but this OH and H are interconverted. Okay, so these are mirror image. Okay, now what happens in this case? First check it. This OH is 1 and COH is 2, anti-clockwise, so S, but hydrogen here, so it is R. OH to COH, it is again anti-clockwise, S, but hydrogen is here, so it is R. Now you can simply say these two are enantiomers of each other. When I say 1, 2 and 3, these two are enantiomers. This is an enantiomeric pair, second and third. Why? Because as you know, this tartaric acid, this is optically active, this is also optically active, mirror image relationship. Now you can observe this S configuration after mirror image converts to R, and here also S converts to R. Means R will convert to S and S will convert to R when it will be having mirror image relationship. Clear? Now we can check from one of the example. So let's take the last example. Now let's see this one. As this is a compound is having a chiral center, it is optically active, and if I draw its mirror image, COH will remain same, Cl will remain same, and H2 will come here and deuterium will come here. Okay, now in this one, if I say this carbon, nitrogen, deuterium and chlorine, 1, 2, 3, you have to observe the first atom first. Here it is oxygen, but it never matters because it is nitrogen and carbon. So if I say this one anti-clockwise using SARC, S, but deuterium is horizontal, so it will be R configuration. Now check this one, 1, 2, 3, it is clockwise, so R, but this one here, so it is S. Now students, you can understand these two bear mirror image relationship, non-superposable mirror images. Okay, these two are optical isomers of each other, and R mirror image will convert to S, and S mirror image will convert to R configuration. Clear to everyone? Okay, so friends, we will continue this topic on our next lecture. See, I have not explained right now about that one part of bond breaking rule, hypothetical bond breaking rule. It will be continued in our next lecture, so keep waiting. Okay, see you in next class.